Thank you. Thanks again to the organizers for the opportunity to be here. Thanks everyone for attending this talk. I'm really excited to be here, to be back at U of T after some time. I want to start by saying that I consider myself to be an unconventional scientist. And part of the reason for that is that I also like to give unconventional talks. So this is an unconventional talk. The whole point of this talk is to make one point. That's my goal. I want to make one point. And to make that point, I'm going to tell you a story. So I'm here to do some storytelling, and I'm going to talk for half an hour until finally I arrive at the point that I want to make. And the story that I want to tell starts with the ending, or the hoped for ending, at least. This is a bit of a cliche internally for us at Xanadu, because most of us start every single talk with the Xanadu mission. I still like to do it, even though it's a cliche, because it does capture very succinctly what the company is trying to do, building quantum computers that are useful and available to people everywhere. Incredibly challenging, incredibly difficult mission, right? However, I don't want this talk to be about Xanadu. I want this talk to be about the community of people working in quantum computing and quantum technologies more broadly. So I actually went through the exercise of thinking, if it were up to me to figure out what a mission statement for the entire quantum computing community, what would that be, right? And so this is what I came up with. The mission for quantum computing is to build quantum computers still that are valuable. And so that's what I came up with. And a big part of this talk is to go a little bit deeper into this word valuable and give you kind of my interpretation of what this means. And so this is crucial for the rest of this talk, so please pay attention. I would argue that quantum computing is right now and will continue to remain very valuable as a contribution to fundamental science. For me, that's the main motivation for the work that I do, is the contributions to science, right? I haven't been in the field that long. I've been here for maybe 10 years, if I'm being generous, maybe a bit more. And already I've seen how it has influenced, and I love this, how we teach quantum mechanics. The ideas for quantum information, quantum technologies have made it into the classroom. We've seen in even talks today how these ideas from quantum computing has influenced condensed matter. They have influenced computational complexity theory and vice versa. We've seen a lot of new insights in quantum foundations, even quantum gravity, right? And even beyond kind of the scientific community and the wider public, quantum computing is fascinating. I remember, like, when I first heard about it, I was fascinated with the idea of quantum computing. It inspires people, it captures the imagination of people around the world. There's a lot of value in this, and I think that's inherently the most important reason to pursue quantum computing. But this talk is not about this, right? This talk is about quantum computing as a technology, right? And so what I mean by this is that, is the following, is that we don't get any points for being quantum. We don't get to be fascinated by the amazing quantum world and entanglement and complexity and inequalities. We don't get points for this, right? We have black boxes that perform certain tasks. And the question is, if we leverage and we build such devices, do we actually then generate value? And that's a kind of a difficult thing to quantify. And so I gave it, again, an attempt, which is the following. And this is what I will mean by value from the remaining of this talk, with the understanding that scientific value is still the most important reason to pursue quantum computing. And it's the following: if it costs X under some measure, right, to use a quantum computer for some task, and somehow you get some benefits, some return, something good coming out of that, right? Maybe some of Y, then the quantum computer is valuable if Y is greater than X, right? And importantly, if Y minus X, so this difference, is larger than what you could achieve otherwise, right? If we achieve this, then we're closer to achieving this mission, not only for the quantum computing, but for example, for Xanadu, right? We're building something that's really valuable, not just because of the scientific value, but because of its inherent direct technological value. And sorry, I spoiled it a little bit. So this talk is telling the story of how myself and the team that I lead and widely at Xanadu, how we're trying to figure out if we can do something that's valuable with a quantum computer. But before I tell you my story, I want to put all of you on the spot and ask you that question. And I'm going to wait for a few, like 30 seconds or so of awkward silence that you actually think about it. If it were up to you, and if hardware is not an issue, we've done it, we've built the devices, we have thousands of logical qubits, we can operate at potentially really fast rates, gigahertz. And now the question is, what do you do with that technology? We've built it, right? What would you do? It's good that we have, what would you do with it? Okay.
Sell it.
But to the what? Okay, so let's think about it. So maybe you actually have some answers, right? Maybe you thought about it, oh, maybe this and that, X and Y. To what level of detail have you been able to answer that question? How much do you know exactly how you're operating, like every part of the algorithm that you're implementing, the problem that you're actually targeting? Do you know the answer to this question? And moreover, if you can do that, do you know how to extract as much value as possible? Can you get that y to be much bigger than x, given the thing that you're using the quantum computer for, right? Do you know this? And I mean, I would argue that this general question, which is the central question that I'm trying to answer as a scientist, what do we do with a quantum computer if we build it? I would argue it's an open problem for the field. I think we haven't really figured it out yet, right? And the main reason for this is that it's extremely difficult to do so, right? So I have a job to do. And it's for various reasons, but one of the central ones, and at least it's the one that it's like harder for us in the team, is that you actually need to do so many things at the same time. You need to understand the application areas, the problem you're trying to solve. You need to understand the classical methods because you're trying to compete against them. You don't want to be naive about this. And importantly, you need to have this incredible expertise in quantum algorithms. So it's inherently an interdisciplinary problem where you need to have extremely high proficiency across a multitude of areas to be able to actually answer this question, right? And so we're taking on that challenge. And just before I tell you our story, I have to do this. I want to quote this paper. It's one of my favorite ones, and people working in quantum algorithms probably know this. I think Nathan Weeb is not here. He's one of the authors of this paper. And I'm going to read a quote from the abstract of this paper, which I really like. It's the following: although quantum chemistry is a strong candidate for a killer application of quantum computing, the lack of details of how quantum computers can be used for specific applications makes it very difficult to assess whether they will be able to deliver on these promises. Right? I'm a big fan of this paper. In my mind, it's the first serious attempt at answering that question: what do we do with a quantum computer that justifies the investment that goes into it in a high level of detail? And so that's pretty much what's also motivating the work that we're doing. Right? So that was the prologue to the story, and this is the story. Right? I'm going to tell you our story in our team in our search for answering this question: what do we do with a quantum computer? What algorithm do we implement that is as valuable as possible? And the way that I want to tell you this story is in terms of a journey that happens by tackling crossroads, right? And really, I want you to understand and to interpret that everything that I'm going to tell you, the directions that we're taking at each crossroad, there's no certainty around it. We're not sure that this is the right way to do things, but it's a strategic bet, right? And that's part of my job, is to figuring out what are the right directions to tackle. Right? So you may disagree with these choices. You may have taken a different path yourself, but it's the story of the path that we have taken. And so every decision that we make at each crossroad is really a bet that we're making. And we're making it because we believe it's the highest chance of succeeding in this quest of finding a valuable quantum algorithm. So where's the first one? It's like, okay, what problem are we even trying to solve? What's the application area, right? And of course, it was actually hard to find images online of several different directions. So I'm kind of narrowing it down to two. For example, do we go into quantum machine learning, right? Do we study quantum chemistry? But really the whole scope, right? And something that I want to share with you is some of the mental models that we use, and that I use, at least personally, in trying to navigate ourselves in these directions in our quest, right? And it's the following: well, if we find the right application area for quantum computing, it needs to satisfy certain properties, right? It should be really impactful to industry. Again, we're trying to generate value, and most of the value that can be generated is not so much at the individual consumer level, but at the level of corporations, and very likely they will be the users of quantum computing if they come online and we can build them. So we need problems that are impactful to industry, really impactful. Second, we need to look at problems that are, roughly speaking, hard for classical. If we can solve them already, then we don't need a quantum computer, right? So we should really be struggling. But of course, there's no shortage of difficult problems that are important, right? We also need that somehow, even though it's hard for classical, we can do it more easily, right? More efficiently, better with quantum. And so that's the goal, right? That intersection of these three things. And this is the mental model in which we filter and assess potential application areas. So, and by the way, it's a bit of a lesson. I've had a lot of conversations with a lot of people. I've seen a lot of work that's happening. I want to share what I think are the main mistakes that people do, which are actually linked to this mental model, is that people that look at application areas, I see mistakes because they underestimate classical algorithms. They don't realize how incredibly good, how incredibly sophisticated both the hardware and the software actually is. So it's actually not that hard for classical, even though you thought it was. Also, overestimating quantum algorithms, right? We can do everything exponential, speed up, it's amazing, it's so good. And sometimes it's not that clear, right? It's actually harder. It's not a magical tool that we can leverage. You have to figure out exactly when you have this potential. And important, and this is really challenging, and this is one of the reasons that I like working in industries. We have a window to what actual companies do, is that it's very easy to misunderstand the problems that people actually care about in practice, right? So you think it's actually impactful for industry to do something when in fact it's not. So this is kind of something I actually pulled out of like some lists. If you Google applications of quantum computing, you'll find some of these. It's not meant to be exhaustive. It's only to make a point, to be illustrating of something I want to share with you. And so we just apply this filter, right? Is it impactful for industry? Is it really challenging for classical? And do we have some foundation to claim that it's actually potentially more efficient or easier to do it with quantum, right? And this is kind of my personal answer to these questions. You can stare at it for a little while, and I'm happy to chat about why this is. But essentially, this is my conclusion. There are some candidates that are weaker. There may be something there, but it's not a bet that we want to make internally. Some others that are stronger. And really, the ones that I'm more convinced have higher potential, and again, it's still potential, it's still not anything that's clear. It's basically factoring. So we go back into the 1990s, we knew this even then, and potentially simulating quantum systems in a context that's actually important for industry, right? Which is largely quantum chemistry and materials. And here, this was also a bit of a business decision. Now it's too broad. We don't want to be as broad. We want to go to a specific place. We want to reach a specific destination in our quest. And so we did choose to focus on batteries. There's two reasons. There's the business one, the potential for generating value. If people can figure out how to build better batteries technology, that's extremely impactful. So if quantum computing can help, and it's a big if, then the impact is huge. But really from a scientific perspective, which is the one that truly motivates me, it's a great kind of, we can get the best of both worlds. We can focus on a specific area, but the algorithms are still very broad because there's so much happening inside of a battery cell. And I won't tell you about this too much, just a little bit, that actually you end up having to figure out how to simulate molecules and materials, reactions, everything in between. So it's a great way of having focus without losing perspective, which is very valuable. Okay, so we're making a first turn in the crossroads. We're going on the right? We're looking at quantum chemistry and specifically the batteries. We're making our first bet. Now, well, it's not a crossroad, right? Now, that's the application area, but now what do we do with a quantum computer? What kind of algorithms do we do? And there's very broad, and there's different ways of thinking about them. More and more people have this distinction, which I think is unfortunate personally, but it is what it is. It's kind of thinking about NISC, so things that are like what we can do right now, and then the fault tolerance regime. And so I'm going to introduce another mental model that I use. Now, do we go left or right? What is the focus? And if we're going to have quantum algorithms that are valuable, that are impactful, then I claim they should be both practical. And what I mean by this is that we should be able to actually implement them. We shouldn't be thinking about science fiction. That we're never actually going to be able to do this. We should be like closer to things that can actually happen. But we should also be performant. So we shouldn't be like naively hopeful that something's going to give us the answers. We should have some good, strong guarantees that this is going to happen, right? And really what we have often are practical algorithms in that sense that are not so performant, and some performant algorithms that are not very practical. It's kind of the reality. And so the work that we have to do is to go into this intersection and this overlap, having both. And again, roughly I would argue the idea behind NISC algorithms is to be closer to the practicality, things that we can do, even if the performance is not particularly exciting. And then you have these fault tolerant, super sophisticated advanced algorithms that are not so practical. And we try to make them more practical, right? And as kind of specific examples of algorithms within these broad classes, people study a lot of VQE, variational quantum eigensolver, and quantum phase estimation as kind of exemplary algorithms in these categories, right? So which one do we choose? Do we choose VQE or do we choose quantum phase estimation? In fact, I would argue that VQE is more like here. Maybe Arthur can have something to say about this. It's actually still very expensive to run even these quantum algorithms. But importantly, and I don't know if Henry is in the audience, the way that I like to think about quantum algorithms for quantum simulation very generally is that you have two main things you're trying to do. You're somehow using your quantum computer to prepare some state of interest. There's some algorithm to do that. And then you extract some information, right? It's not enough to have just some quantum state lying around. You need to kind of read something out of it. And it's that second part that's particularly tricky. And I think it's very underestimated. And in fact, I asked this question in interviews. People that want to work with me, I asked that question, right? Suppose you solve the state preparation problem. How do you compute even something like an expectation value? How do you do it efficiently, right? And Henry was saying, well, just use quantum phase estimation. That's the thing to do, right? And it's, for those of you that are maybe not experts in the field, quantum phase estimation has this reputation of being extremely challenging, like extremely complicated algorithm. But in reality, we don't know much better than quantum phase estimation, especially for large systems, and especially when it comes to extracting information, right? It's still an algorithm that has a lot of problems, and it's a family of algorithms, as I'll tell you in a moment. But for these reasons, that's the direction that we're taking, right? And importantly as well, we want a more solid foundation from the scientific perspective, that at least there's some performance guarantees, or at least closer to some performance statements that we can make, and then we build closer to the practical regime, right? So I want to start, maybe I go back quickly. I'm more motivated to go from performance to practicality than rather the other way around. But again, that's a strategic bet that we're making. Okay, so we're getting closer, right? And now, so what type of quantum phase estimation algorithm, right? There's a lot of ideas. THC is not what you think, it's tensor hypercontraction, but it's kind of exemplary of different ideas that people have figured out, right? This is the more technical part of my talk. Now it's a lot of decisions that have to be made in how we represent systems in quantum chemistry, etc. So there's like, do we use first or second quantization? What kind of basis set? The fermionic to qubit mapping? How do we, it's quantum phase estimation, so we're encoding a Hamiltonian into a unitary. How exactly do we do this? There's a lot of different techniques that people have studied. So we still have to figure out, I mean, again, we're trying to have details, right? I want to say, how exactly are we programming the quantum computer to extract value? So we have to go to that level of detail and figure that out, right? And really, we were persuaded that this paper, that again has Nathan Weeb as one of the authors, and it's a collaboration between Google and our academic people, that introduces some first quantization methods in a plane wave basis using a qubitization encoding. So these are technical terms for the experts, but just so that you know. We were convinced that, especially when it comes to material simulation, this was state of the art, right? This is the best quantum phase estimation for our purposes in batteries. And if you're curious, the main idea is that using plane waves is fantastic, has so many advantages in the context of materials. But if you're not using first quantization, you're in trouble. It's really prohibitive, right? And in particular, if you need high accuracy, which is what we're trying to do in the context of quantum chemistry, then qubitization is typically unmatched as the way of encoding Hamiltonians. There's one drawback, though, is that initial state preparation, because you have to explicitly anti-symmetrize, it's really, really complicated, right? But that's the direction that we're taking, right? We're persuaded that this is the state of the art. All right, so we go to the left now, right? And so now we're getting closer. And did we just make it? Did we make it to the promised land, right? The quest is completed. We're here, right? We're doing quantum chemistry, looking at batteries. We're looking at quantum phase estimation, and we have a very specific state-of-the-art recent algorithm that has a lot of amazing features, right? So that's it. Like, we answered the question potentially, or that's what we want to know. And so we answered that question, right? And I said, I'm an unconventional scientist. I like to think of myself. This is an unconventional paper as well. I still don't know how to describe it. It's somewhere between a review paper, a tutorial, sprinkled with some new results, and comprehensive across different disciplines. And the reason is that we were really just trying to answer that question. How do you simulate important properties of a battery on a quantum computer, right? Again, very motivated by the importance of details in answering that question. I want that if my colleagues at Xanadu build a quantum computer and we build a software stack around it, I want to tell them this is what you do with that device. I want to tell them exactly what that is. And it's really hard to do so, but at least we're trying to do it explicitly and seriously, right? So if you're curious, this is the paper, and I'm happy to discuss it. Really, it's an application of this technique, right? So we're really leveraging that algorithm. We're not developing the algorithm. We're like filling in some gaps, but really that's the work that they have done. And so we do it. We explicitly mention how people do this. What are the setbacks? What are the important questions? What are the properties that people actually care about in in simulating batteries? How exactly do you implement this algorithm gate by gate? How much does it cost? What we can expect? We do it for a specific realistic material. And this is a summary of what we find, right? So just a technical thing. These algorithms are so sophisticated, you need so many gates that absolutely you need error correction and fault tolerance. And in quantifying the cost of a fault tolerant algorithm, typically people look at what are called non-Clifford gates, which the Toffoli gate is an example. So that's why this y-axis is the Toffoli gate cost. This just means this is a standard way of quantifying the cost. Why the non-Clifford? They're just much more expensive to implement in a fault tolerant setting. So they capture the cost of the computation, right? Now, in first quantization, like I mentioned, state preparation is very challenging. So we actually take a look at that. And we find that it's still really difficult to do the state preparation. It's a drawback of first quantization, but it's much smaller than the entire algorithm. So we kind of confirm that with a specific recipe to how to do it, right? And the numbers, and you need thousands of logical qubits. That's how it is. And you look at the y-axis, we're talking about billions, maybe trillions of these gates. That's the state of the art. That's where we are at now, right? And you may be wondering, well, I mean, but that's this algorithm. Maybe you just took the wrong path, right? But again, this is similar, and I just want you to focus on the y-axis in this plot, right? So look at those numbers. This is from that same paper that we're using. They do some different calculations in different systems. They get similar results. That's no surprise. We're still leveraging their algorithm. You can look at this as work from some of our competitors inside quantum. It's really great work, taking a very different approach from us, and still that y-axis is very high, right? There's also work from Google in collaboration, I think, with Boehringer Ingelheim. They're looking at a specific kind of system that's important in pharma and how it relates to the human function. And they have a different y-axis where it's time, not so much gate costs. There's more speculation in that because you have to anticipate how fast your quantum computers are. But you still see, potentially to simulate a system that's really challenging for classical. The classical are the blue ones. You'll be probably needing hundreds of hours to get there, right? And so there's a lot of challenges. Again, I have a job, right, to do. Initial step preparation, if you encounter this and if you think of conference estimation, this remains one of the open problems. Can we actually prepare ground states that have a sufficiently high overlap with the ground state? This is important for that algorithm, and also in a way that the classical methods don't give you already a good answer for what you want, right? Now, internally, because of our expert understanding and all the effort we have put, we're confident that we can reduce the cost, so those numbers can come down, and they have been going down steadily over time. It's just not clear by how many orders of magnitude for quantum phase estimation, right? Like I say, we're not going to reduce it down to one gate. That's never going to happen, right? But is it 10 to the 10, 10 to the 9, something else? It's an open question. And when you want to simulate materials, it's particularly difficult, right? It's something we have learned. One reason is that you require often a supercell treatment with many, many electrons. And that's actually, for technical reasons, an additional argument in favor of plane waves and first quantization. So I'm very convinced that if you want to simulate materials, you probably have to do first quantization in plane waves, unless we have some additional breakthrough, right? And so this leads me to like my final mental model that I want to share with you, is that, again, thinking very carefully about what to do with a quantum computer, right? Is that at least in this context of quantum chemistry and material science, it's not the case that there's a problem that you just throw it to the quantum computer and you get the answer and then you profit directly. It's not like how you would do this with factoring. You just break the encryption and you factor your numbers, you break RSA. That's just not how it works, right? Because, for example, the challenges that people face in developing better batteries are just more complicated. They're not well defined into a single computation that just has to be solved. It's really figuring out like new ways of designing materials and the interactions with them and scaling them and fabricating them, etc. So really, like what I'm convinced we can potentially achieve is that we increase the chances of people to actually come up with these breakthroughs, right? Because they have access to potentially powerful simulation techniques, right? And so I think there's real value in this. This is something that can give you this y minus x thing that you want and people can actually pay for. But it looks very different. Scientists still have to use their brains, even if we have better quantum algorithms. Okay? And so that leads me to the point that I wanted to make. I just spoke for half an hour to make this point, which is that we need even better quantum algorithms. It's an important problem central to quantum computing, right? We still have a lot of work to do in figuring out how to have more efficient, more clever, more sophisticated ways of programming quantum computers to solve important problems, right? And of course, we also need to build fast and large quantum computers. With that said, thank you so much. And if you're interested in joining and doing this kind of work, well, we're hiring and I'm happy to talk about it. Thank you so much.